All right, section 3.3 is going to feel a lot like 3.2. We're going to have a lot of the same things come up over and over again and between these two sections, a lot of similarities. The difference is, of course, we're going to be working with multiplication, division instead of addition, subtraction. We're still working in the whole number system, so 0, 1, 2, 3, 4, and so on as we work through these. And I think we will be able to get through probably the multiplication section today, and then we'll be doing the division one on Wednesday. I think that's how it'll work. So let's give it a go and see how it goes. All right, to start with, multiplication of whole numbers. So for finite sets A and B, if the number of items in set A is lowercase a and the number of items in set B is lowercase b, then when we talk about n times A, it means A plus A plus A plus A, like repeated addition, n times. Now, if n is equal to 0 instead of being not equal to 0, like on the first bullet point, then we're going to define 0 times a to be equal to 0. And then if we multiply a times b, that is the number of items in set A times the number of items in set B, that is actually equal to the number of items in the Cartesian product. And we actually saw that property once before when we looked at the Cartesian product. We saw this formula come about. Okay. I'm going to talk through the multiplication models, and then we have an odd number of people today. So we'll have one group that has an odd number of people, and everybody else will be in pairs. We're going to do the same thing we did with subtraction. You guys remember where I had you create examples of word problems using those properties? So let me talk through with you the versions of what mine are first. All right, so the first model for multiplication is the repeated addition model. The idea of repeatedly adding something together over and over again. Giselle takes 3 tests every Friday. After 4 Fridays, how many tests has she taken? Okay, so this idea of repeatedly adding the same number to itself, which is very much like the definition that we saw over here on the very first example, right? A plus A plus A plus A. Okay, this is a model for multiplication. So if we took 3 tests every Friday, and we actually did that for 4 Fridays, this is physically what we were doing. Of course, this is the same thing as 3 times 4, and we would have 12 tests. Now, sometimes you'll have a picture where it'd be something that you could actually draw, and so you have a concrete model where you're drawing something. So like, if I ate 3 cookies every Friday, could I draw a picture where I have 3 cookies and then 3 more cookies and 3 more cookies? And sure, absolutely. I don't want to draw tests. That seems a little bit funny to draw, but we could do that. Okay, so we definitely could have a model where we're drawing out the concrete version of this as well. So repeated addition. The second one is array. An array model is definitely used for sets. Minhyu is baking cookies. He is able to place the cookies 3 cookies wide, place the dough 3 cookies wide and 6 cookies long on his pan. How many cookies will his pan hold? Now, this isn't really the same as the one before, right? It really has a visual imagery that looks like an array. So when we're thinking about drawing this picture, doing the example for this, and it is cookies, we are supposed to be drawing, oops, hang on, let me fix that. We're supposed to be drawing our example, let's say, to say 3 wide. Yeah, 3 cookies wide, right there. And 6 cookies long. So we're going to do 3 wide, and then 3 wide again, and we're going to keep going until we have 6 long when we're doing them. So here's my 3 wide, and here's my 6 long. And so I'd end up with how many cookies? 18, right? That's different than doing something repeated number of times, 3 to 3 every week. The next one is an area model, and the area model is very much like the array model. It's just that it's used for measurement of things. Okay, so the picture we're going to see with this is going to feel like, oh yeah, it's length times width again. right? I mean, that's what this looks like. I've got the length 3, I've got the width 6, right? Or vice versa, width 3 and length 6, however you want to describe it. The area model feels that way too, except that it's measuring it in terms of lengths of something, not physical objects. Alexis is planting. I guess we could say planting a garden, it would work. She's planning to plant a garden. She has space that's 5 feet wide and 7 feet long. How much area does she have in which to plant? So our picture ends up looking like what shape? A rectangle, yeah. So I'm going to plant a garden. It's going to be a rectangle, and it said 5 feet wide, 7 feet long. My picture looks like the length and width are switched, but that's okay. Here's my 5 feet. Here's my 7 feet. And if we wanted to actually do something with like counting arguments here, we could actually divide this up as well, right? Okay, they should be even. Mine are not. But there's 5 feet. They're marked off in 1 foot sections, and I could do the same thing on my verticals. Again, they're not perfect, but if I've marked them off well enough, I could actually count the number of individual 1 foot sections, right? I could. And then the area then would be a total area of what? Good. 35, and Amy's exactly right. It's square feet or feet squared. So this is what we would have. Okay, so the difference between this and the other one is that I'm measuring a length on the length and the width, right? I'm not measuring actual objects. Do you guys see the difference? This is used for measurement. The other one's used for physical objects or sets, concrete single things. All right, so I'm going to put you guys into, in fact, let's see who's here today. Hang on. Take about 1 more minute to finish up your third model. I think everybody's doing area at this point. Lauren, Jasmine, Rose, are you guys on area? Okay. Okay, so we're going to go through these like we did last time. So somebody offer up to the class, what did you write down for your repeated addition model? One of the groups. Amy?
We put if you eat 2 apples every day for a week, how many apples have you eaten at the end?
Excellent. 2 apples a day for a week. How many have you eaten at the end of, what did you say? 1 week. Okay, great. All right, that works, right? Yeah. All right, how about array? Somebody do array for me. What y'all choose? Okay.
We did Nathan's Hot Wheels box can fit 4 Hot Wheels wide and 8 Hot Wheels long, and is the shape of a rectangle. How many Hot Wheels can fit in Nathan's box?
Fantastic. Okay, so that's a good visual imagery, young kid kind of application. Nice. All right, what about area? We've got 2 groups left, but who's going to talk?
We put that because mom is making a sandbox for her. It'll be 5 feet long and 5 feet wide.
Great, so we've got the area of our sandbox. So Lauren, Jasmine Rose, tell us what one of yours was. I don't care which one you picked. Just pick one for me and tell us what you chose.
Corey is building a rabbit pen. She has enough fencing for 10 feet wide and 5 feet long. How much area does she have for a rabbit's pen?
Okay, so we're in the third model, right, with the area model. Okay, so I want you guys to brainstorm with me before we leave this section because array is the one that I find the most interesting of these models. So think of objects in your surroundings. So we got the Hot Wheel box going on over here of things that occur in arrays. There's lots of them. So can you think of any?
Desks.
You could do desks in a classroom, right? Yep, that would work. What else?
We did Legos.
Parking spots in a parking lot, that would be true. What else did you
We
have?
did
Legos. Okay, good, Legos.
Flower seeds.
Yeah, so like maybe when you're planting, so like we did the example of planting with area a minute ago because we planted in terms of the square footage in our garden, but you could do the flowers in the garden themselves, and that would be an array model, right? How about things like a muffin tin? That works even better than cookies because it's forced to be that way. How about 24-pack of soda? How about the can aisle at the grocery store? Like where you see all the, cans of green beans or whatever. How about the toilet paper? How people buy toilet paper? You know what I'm talking about? It's 2x3 or something like that, and you get 6 rolls in the thing. There's lots of objects that we actually put into arrays. All right, let's look at some whole number properties of multiplication. So we did whole number properties of addition, and we talked about how they don't work very well for subtraction, so now we're going to do multiplication. Closure. We get closure again. Closure says that for all whole numbers, A and B, if we multiply 2 whole numbers together, we get another whole number. Okay? In other words, you can't multiply 3 times 2 and get a fraction or get a negative, right? That doesn't work. You get another whole number. Commutative. With addition, we had the ability to say that 5 plus 3 is equal to 3 plus 5. We have that same ability with multiplication. 5 times 3 is equal to 3 times 5. Multiplication is commutative. You can switch the order. Yes?
On the closure property,
Uh-huh.
it says that A times B is a unique whole number.
Right.
Does that mean that it could be A or B? Or does it have to be a completely different number?
It could be A or B. Unique simply means that the product is a specific answer. You can't say something like, oh, and it has 2 possible answers.
Okay.
Right? Like there are some properties in mathematics, when we do them, we get 2 answers. For instance, if you were solving an equation like x squared equals 1, the answer is 1 or negative 1. It's not a unique answer. This one is. You will always have a unique product when you take the 2 values. It will have a unique answer. All right, associative is next. Associative has to do with grouping of things, right? So like A, B, C is in the same order on both sides. On the left, it's the A and the B that are grouped together. On the right, it's the B and the C that are grouped together. It's what's associated, which part of the equation you do first, or the expression you do first. Do you do the A times the B first, or do you do the B times the C first? And with associative property holds, it doesn't matter what you do first, and multiplication has that property. This one right here is we had the additive identity before. This is the multiplicative identity. So where it says identity property, this is an identity property for multiplication. So whenever we identify this property as being used, we're going to call this the multiplicative identity. But the word multiplicative needs to be on there. What was our additive identity value? 0. So the multiplicative identity value is different. It's the value 1. It's the value such that when we multiply it by something on either side, so A times 1 or 1 times A, we don't change the value we're multiplying, the A. Okay? It becomes A just like it was before. We have a couple of more. We have the 0 property. The 0 property says that A times 0 is equal to 0 times A, which is equal to 0. That is a unique value that does that. No other number does that for us. And then the distributive property combines multiplication with addition and subtraction, or addition or subtraction. So if you have A times the quantity B plus C, or times the quantity B minus C, it's the same thing as AB plus or minus AC. And you often will see people draw like this, right, when they're distributing the A over the parentheses. All right, so what we're going to do is we're going to look at a list of 1, 2, 3, 4, 5, 6. There are 6 of these. I'm going to let you give it your whirl, give it your best guess as to which ones they are. Which property is represented in each example? After you've written down which one you believe that it is, I want you to turn to a neighbor and confirm with them that they and you have the same solutions. And if you're not sure, talk about it until you can come to a consensus. We're good? Awesome. Okay, let's go through these together. If you don't quite have them all finished, or if you're not sure, we'll double check, make sure everybody does. What is the first property you guys think? That is the 0 property. What's the second one? Commutative. And we talked about this last time. Just because you see parentheses, don't think that automatically means it's associative or even distributive, right? Because we've got 2 possibilities with parentheses now. Because what actually changed is the order inside, the 4 times 3 and the 3 times 4. How about the next one? That one is associative. On that one, we have the 7, 3, 4, the same 7, 3, 4, and it's the parentheses location that changes. First one is around the 3 and the 4, the second one's around the 7 and the 3. How about D? That is the multiplicative. I'm glad you guys said that. Multiplicative identity. If you left off multiplicative, go ahead and add it in right now. Multiplicative identity. How about E? That's the distributive property. What distributes?
The 5.
The 5 does. So the 5 is distributing to the 3. The 5 is distributing to the 4. So it doesn't have to be a 5 written in front to do that, right? F is a little weird looking, but can you tell what that one is? It's also distributive. What distributes? The 1 plus 2. So this quantity as a whole distributes across. So you end up with 1 plus 2 times 3 and 1 plus 2 times 4. Any questions on those? All right.